We've all learned about exponentiation in school. It's a way to express repeated multiplication in a compact form. It involves two key numbers, the base x, the number being multiplied, the exponent n, the number of times the base is multiplied by itself. In short, exponentiation simplifies long multiplication into a much cleaner expression. At first glance, this might seem like the most efficient way to calculate powers, but actually, it's far from optimal. This method is called naive exponentiation for a reason. Let's take an example. Raising 2 to the power of 10. That means performing 10 separate multiplications just to get 1024. More generally, for any exponent n, this approach requires n multiplications, which can quickly become inefficient for large numbers. Here's a visual representation of the naive exponentiation process. Since our base is 2, each multiplication doubles the result. If we used base 3, each step would triple the result instead. What if we could compute exponents much faster than the naive method? That's exactly what exponentiation by squaring does. There are several ways to apply exponentiation by squaring, but in this video we'll focus on the basic recursive method. This method follows two different formulas, one for even and one for odd numbers. If n is even, we can simplify the exponentiation like this. If n is odd, we first extract 1x before simplifying. In the end, both formulas simplify back to x then, but in a much smarter way, reducing unnecessary multiplications. How can we compute 2 to the power of 10 efficiently? Let's break it down using exponentiation by squaring. We will keep track of values x and n. In the first step, n is 10, which is even, so we use the even number formula. The result simplifies to 4 to the 5th power. Now let's update x and n. N is now 5, which is an odd number, so we use the odd number formula. The result simplifies to 4 times 16 squared. Now we have a number with the exponent 1. At that point, we don't need to continue the algorithm further, but let's try to do it to see what happens. Update the values for x and n. N is equal to 1, which is odd, so we use the odd number formula. This simplifies to 16 raised to the 0 power. Anything raised to 0 is equal to 1, and anything multiplied by 1 is equal to that same thing. So we are back at the point where we started. The algorithm stops at n equals 1 because we've fully broken down the exponentiation. There's no need to continue further, as we already have the correct multiplication structure. Let's handle the 16 squared. Update the values for x and n. N is equal to 2, which is even, so once again we use the even number formula. This simplifies to 4 times 256, which is equal to 1024. And just like that, we've computed 2 to the power of 10 is equal to 1024 in just a few steps. We've now seen how exponentiation by squaring works, breaking numbers down step by step until all exponents of factors become 1. This confirms that we've correctly computed 2 to the power of 10 using exponentiation by squaring. Now let's visualize this process step by step. 2 squared becomes 4. 4 squared becomes 16. 16 squared becomes 256. Finally, we multiply 4 times 256 to get 124. Now let's compare the two methods side by side. Both computed 2 to the power of 10, but how many steps did each one take? Naive exponentiation, 10 multiplications. Exponentiation by squaring, just 4 multiplications. That's because naive exponentiation grows linearly. The bigger the exponent, the more multiplications you need. But exponentiation by squaring grows logarithmically, meaning it handles huge exponents much faster. That's why exponentiation by squaring is used in all programming languages for integers. It's exponentially faster and scales efficiently.